Hey there. You might have come across the news that Australia has very recently, like about a week back, announced that it's going to ban the usage of social media for anyone under the age of 16. So, if you are up to the age of 15, you will not be able to use a lot of social media. There are still a few channels that are going to be accessible, um, like YouTube Kids, for instance, but most of the social media, like regular Facebook or Instagram uh, so these channels will not be accessible. So the question naturally came to my mind. I mean, there's already been a lot of buzz around it, like what's going to be the effect of it from a social or a mental health perspective. But I'm obviously not going to go into that. What I was thinking about, what could be the impact of it from a business point of view. Now, we know that these social media channels, of course, don't give a lot of data for they don't give mostly any data at all for minors, anyone who is below the age of below the age of 18 even, and certainly not below the age of 16. So data is a problem, but there can be ways of having that data. I mean, again, the ethical implications of the same is there, but just from a research interest point of view, I was thinking, if we were to be able to understand get the data, and how would we then proceed to understand the causal impact of this policy change on businesses, so in terms of revenue or other things. So we'll look at some causal questions and then a particular method. So this is the news item that we are talking about: Australia banning social media for kids under 16. And there's tons of material on the net if you just want to look at the news item itself. So here's the problem at hand: evaluating the causal impact of the recent ban, effective from somewhere around the 10th. And it's a high value econometric challenge, because causal inference and causal techniques are mostly born out of the econometrics background. So this is a this because this policy is a natural experiment constrained to specific geography and demographic, it is perfectly suited for quasi experimental causal inference methods. So Australia and 16-year-olds or below. So here are some possible causal questions. Like, I was exploring, first of all, what kind of questions would come up. So one of the questions could be like, did the ban cause a decrease in total digital ad revenue for brands targeting Gen Z in Australia compared to other regions? So this can be a very interesting causal question, of course. And one possible method would be synthetic control methods, which is where you create, which is where, for the regular vanilla SEM, at least you have one single treated unit, and then you have a constructed synthetic comparison unit based on a weighted combination of similar countries, depending on which are similar to what extent, and that will mimic the ad spends before the ban. The divergence then would basically give the causal impact. There could also be questions like, did the ban actually drive a migration of user attention to unregulated platforms? So, for instance, whether Discord or Roblox, these could be, like I said, there are some social media channels which are still going to be left out of this equation of this ban, and this can be a possible method. Is again, feel free to share in the comments if you have any, if you are from causal inference or econometrics background, and if you have a contrarian view regarding the methods for these questions as well. But interrupted time series seems like a good idea here. And if you lack a perfect control group for unregulated platforms, you can look at the trend of active daily users on platforms like Roblox. A sharp jump or break in the trend line precisely at the implementation date might suggest causality. And then the question that we are actually going to look at in this particular video, in this exercise, using a simulated or dummy data, where we try to answer, does answer the question: does losing social media access cause a drop in online impulse buying for 15-year-olds compared to 16-year-olds? So the possible method here, this is something, again, this is actually something that I'm making after sharing a LinkedIn post. It a lot of people interacted on it, and a lot of people from marketing and from data science have also taken interest in it, and a lot of them have suggested different methods. But one of the methods that I originally also thought of was regression discontinuity design. um, so So the way it works is, there's a sharp cutoff, and again, so there are actually two types. I've not mentioned that, but in this document, but there are actually two types. There's a sharp one, and then there's a fuzzy one. For RDD, when there's a sharp jump, that's what it's called, a sharp RDD. But anyway, so here you can compare the purchasing behavior of users just below the cutoff, as opposed to those who are just above it. So it's like a very quick change. That's what we're going to try and see if there is any. That's the whole point of this exercise. So obviously the simulated data will be created in such a way so that we do observe such a shift, or such a jump. These two groups are effectively identical in maturity and habits. The only difference is the band. So the reason why we choose 15 years 11 months and 16 years 1 month, for instance, like very closely overlapping, but they're just, it's at the policy level only, because at a policy level, for just 1 month difference, it makes all the difference, because the people who are in this range, for instance, just below the cutoff, they are still able to use they are not able to use social media, but these people are. So that's the point, and in all other respects they are mostly similar. That's the assumption here. So why is RDD ideal for this question? So the birthday is immutable, you can't manipulate it. It's a very important thing. We'll see that we actually need to do a test also to check for it. And then there's a sharp policy cutoff, clear treatment assignment, because it's obviously only directly targeted at 16-year-olds. There's no ambiguity there. Um, or people below 16-year-olds rather. And the fact that there's no parallel trends requirement. So there's another method called difference in difference, for instance. It's much more important to look for parallel trends, the violation of which will mean that DID cannot be used for causal impact estimation. But in this case, it's not really required as much observational data. You don't really need to run proper experiment, although it's kind of like a natural experiment. We just started off with that discussion, but it's going to be still quasi experiment, and you're going to be using observational data and clean identification near cutoff. And one of the concern, of course, is whether or not this can actually be enforced. So that question also came up, during the course of discussions on the LinkedIn post that I shared originally. People were asking, whether or not this is even ethical, or even, you can actually collect this data, or whether you can really enforce it properly, because people below the age of 16 might still actually find out ways of actually, gaining access to social media. Some are even asking, whether or not if they actually even spend a significant amount of money for an effect to be detected. If they at all spend money, because we are trying to understand the impulsive purchasing behavior. Remember, that's the impulse buying behavior, which means basically usage of social media, and people, when they see ads, there's an impulsive reaction to it. And whether this will basically be, something that will hold or not. Okay. So what is the kind of but yeah, I mean, these concerns are there, but this is, again, like I said, this is obviously not based on real data. This is simulated exercise. And yeah, those questions do stand. It's not that there is any resolution around those, but we are just, obviously, for the purposes of this exercise, just assuming that um, the assumptions do hold. So this is the data, the simulated data that we are going to be using, like n equal to 2000 simulated teenagers, running variable. So this is a variable essentially where, which accounts for, on which the threshold is going to be applicable. So this is going to be the days from birthday essentially, and this is minus 180. So basically 6 months on either side of the 16th birthday, because that's the intervention point. Treatment, social media access, we all know, 1 if it is greater than 16, less 0 if it's less than 16. Outcome, monthly impulse spending. True effect being, we do know that there's actually a 25, this is in k, you can imagine, like in thousands, or in millions. So 25,000 per month increase from social media access. And structure is linear age trend, and there's a discrete jump and then some random noise. So we're going to actually look at the output, and before looking at the statistical results, this is what the simulated output actually looks like. This is this is of course done using Python. I'm not walking through the code here. I'll actually leave the link to the code. So the Colab link, if you want to take a look at that. but I'm just walking through the output that's been obtained. So this is the social media access driving impulse, the impulse behavior analysis, and as you can see, this dotted line here, that's what represents the 16th birthday, which has been taken as the sort of centering. So that's why that's zero, and on the left hand side we have people who are less than 16. On the right hand side, which we have people who are above 16, and they obviously have the ability to access social media. And see that at this very point, where we remember we assume that um where there is an actual sort of continuity in terms of every other feature, every other aspect of the individuals except for the ban imposed on the people on this side of the line. So that's why we see that there's a jump here, and this jump therefore and this jump is in terms of with respect to the impulsive buying, the spend, or the the purchasing behavior. So therefore it's only attributable to the policy difference, and these are the statistical results. So this is the effect, and with a bandwidth of 90 days, we have a 95% confidence interval between these two values, and a very highly significant p-value. So there you go. This is the different set of other graphs. The first graph we have already discussed. Then we also have a bin scatter plot, which basically uses like a bucket of 10 days. So it's as you can see, there's a mean impulsive spending for 10-day periods. So that's why we have fewer dots here, just for better understanding the distribution of running variable. Now this is very important. This is basically your manipulation check, and we run what's called LC, a McCready test. A McCready test basically gives you a test for manipulation, whether or not people are saying, whether or not they're just faking their birthday, right? And so the idea is that this should be fairly like equally distributed, fairly smooth, and no specific bunching near the dotted line. So if you look at the validation point here, so this validates a key RDD requirement, that individuals cannot precisely control their position relative to the cutoff. So that's a very important point, that people cannot just lie, and therefore there's not going to be any bunching around the dotted line, which just shows that this test has been passed. And then there's also this bandwidth, which just shows then that it should be fairly continuous, and there's no special departures from the trend, and it's trending and averaging around that 23 mark, as you can see from the y-axis. This is again a very similar thing, showing the similar thing, but just in the form of a box plot, showing the distribution. And as you can see, for people who are allowed, like above 16, they're obviously they are averaging the monthly spends around somewhere around 80 to 90, and these people are averaging somewhere around 40. And so you get how the distribution is basically looking like. And then you also have the rolling mean, which have been plotted here instead of just the point wise ones over each day. So this is how the graphs have been described as well. So you can just take a look. This document will be there, by the way, in the YouTube description. And so the bandwidth robustness, as I said, the treatment effect estimate using different bandwidths, and checks if the stable the results are stable or not. So that's pretty much it, and you'll see this last one here actually shows the jump as well, like has been mentioned here. This is basically a kind of a local average, because you're taking the rolling mean. Now the question is, what the math really looks like. So this is where we jump into a little bit of math. I'm not going to go into very technical details here, but just basic equations. So the basic setup is this is the indicator. So it just shows whether or not the treatments or the treatment, so this is basically given by um, the treatment, whether or not the treatment is being given, is basically given by whether or not this running variable r is actually greater than a threshold value. And if it is greater than a threshold value, then you get 1, otherwise it just says 0. So the di is nothing but it takes only two values, 0 or 1, depending on what the value of the running variable, which in this case is age. And so that's basically your setup equation. And then you also have, or rather your setup yeah, you can say equation. And then you have a continuity assumption. So remember, that's what we said, that the whole point of RDD is based on the fundamental assumption that that if the points are very closely together, very similar to very close in terms of their actual values. So someone who is of 15 years and 11 months and someone who is 16 years and 1 month, they are very similar in pretty much everything else, and therefore they are very comparable except for anything that's externally imposed, like in this case, which is the policy ban. So the continuity assumption therefore says that the limit, the expectation of this observed output for all the individuals at a specific time, given that the running variable takes a particular value, and this is coming from the left and this is from the right. And from the left simply means that people who are under the threshold, and this is people who are above the threshold. So the expected value, if it is tending towards that threshold, which is C, this coming from the left, this coming from the right, they sort of tend to be almost equal. So that is the continuity assumption. And so basically, in plain language, if you're not so much mathy and you want to avoid that, what it means is that if there were no treatment, outcomes would be smooth through the cutoff. Now, treated potential outcome, approaching from the left, like I said, and then you have the control potential outcome, and then you have the continuity assumption presented in this form. So, by the way, this is also the identification assumption. There's something called identification in causal inference methodologies, meaning that whether or not if that can actually be answered properly using causal methodologies. And then comes the question of the estimation or the effect identification and the causal effect at threshold. Therefore, so these are exactly the same terms that we just saw here for the continuity assumption, but the only difference here is that we are now taking a difference because we are trying to understand in real life, of course. Even though they are very similar, and the whole point is that there's going to be a difference because of the policy intervention, for instance. And so what we do here is, instead of writing it in terms of the observed output, we actually use now the potential outcome. So now we have gone to the potential outcome framework, where we use the concept of the counterfactual, going into core causal inference territory, basically. Up until now was a simple representation in expectation terms, basic statistics. And you'll see that instead of this yti, now we have y0i, because this means that this is basically for the same unit, for the same ith unit. If we have like observation, the observed output for the same unit, given that it received a treatment, and then subtract from it if it did not receive the treatment. And the difference between these two, of course, we don't have, like, if this is a treated unit, we don't have the value of this one right on the right hand side. But that's where the counterfactual comes into the picture. But we can basically replace it, because that's what RDD is like. We can just replace it with a value which is very close to it in terms of age. So that's how we can get the potential outcome. And we take the difference because of the continuity assumption. The limit goes out of the window here and takes this form, and then we obviously have the property of expectation, which is why we can reorganize it in this format, which is where the expectation of the observed outcome, given there was a treatment, and if there was no treatment, the potential outcome, given the conditional being on the specific value of the specific value of the running variable. Now the equation that you actually see, this is where we use the concept of dummy variables, and we actually construct something. So the way this can be answered, so right now this was still in the potential outcomes framework, which is using expectations. But how do we translate that into a model which is solvable? And that is again using good old OLS, essentially. And what you see here in front of you is nothing but OLS, where you have the beta 0, which is the main intercept, but you also have like the running variable coefficient beta 1, and Ri being your running variable. And then you have this actual treatment effect being represented by the coefficient beta 2, and then the indicator here, like, which is 1 if, like we discussed before, the running variable actually meets the threshold, or is 0 if not. And then another one, which just gives you the different slope after the cutoff point. So essentially the interaction term here. So that's another coefficient beta 3. So that, solving for this basically gives you the different values of the different coefficients, and ultimately takes this form as well. So if we were to rearrange this in our form, in for our example, this is how it will basically look like, where you have yi, which is your observed value. It's going to be in the form where you have an intercept, and then you have the coefficient, and running variable being age, and then you have beta 2, and then that indicator where it's either going to be 1 if it's above the threshold of 16, or it's going to be 0 if it's not, and then that interaction term, and beta 2, like we said, this is basically your causal effect, which comes out to be somewhere around 23, and which is very close to a true effect of 25, remember. Right. So pretty close estimate. And this was, of course, like a simulated data. This was done just to understand what could be a possible method. uh, there were others, like I said, on LinkedIn. I got people were suggesting combining this maybe with difference in difference. Some were suggesting ITSA as well, like interrupted time series. So there can be multiple ways of attacking a problem. But one of the powerful things of regression discontinuity is its simplicity, right? I think it's incredibly simple. It does not even require the no the parallel trends assumption. The only main assumption is that things are very similar. Now, important questions were there as well, and these are very valid questions. If truly people who are just under 16 and just above 16, they are really similar in every other way except for the policy difference. Like, is there anything else that could potentially be confounding their impulse buying behavior? Any other kinds of accesses, like like driving licenses or anything else at all that could potentially also cause differences. So those are also questions. Anything, any discussion or any analysis of a magnitude of this level, um, of a policy level intervention, is always going to have different kinds of implications, and it has to be explored from different ways. Even for the data collection part, it's so complicated. But just wanted to also, like, obviously the topic itself is interesting, but also the method is interesting, so I just wanted to explore it. And I obviously make posts on econometrics and marketing measurement, basically, and using econometrics methods and causal inference methods. So if you are very interested in these things, if you are like a CMO or a brand manager, or running an agency, and you're looking to upgrade your understanding of marketing measurement, you can follow my channel, my YouTube channel as well. So hope this was useful. If you have any questions, any suggestions, any anything that you feel constitutes omissions or commissions, anything at all, just feel free to comment. Always up for some good discussions. But thanks for watching.